Morning, everyone. The next several days, we're going to be working with a very popular type of distribution, one that even if you haven't seen it in a math class, you've seen it probably in a science class or a social science class like a psychology, because it basically helps us explain and find probabilities and kind of predict probabilities when we have data where the results represent something that is kind of random and normally distributed. If something is normally distributed, it's basically a situation where more or most of the data is close to a mean, and it tends to spread out as we go away from the mean. The visual of this, of course, is the bell curve or the standard curve. Mathematically speaking, however, it's this function. So if we have a normally distributed function or a random variable, then its probability density function is going to be f of x equals 1 over sigma radical 2 pi e to the negative 1/2 2 and raised to the x minus mu over sigma, the whole thing squared. So it's rather complicated, realizing this is your only variable. That is your random variable. So we have to know the standard deviation, and we have to know the mean. So if for some reason you would grab your calculator and put some numbers in for these, you could go ahead and verify that the area under the curve from negative infinity to infinity would actually be 1, and that is a requirement for a probability distribution. One bit of notation for this is simply that x would take on a normal distribution, mu sigma squared. So when we see this, we also have some good information. Now, here are a few things in terms of calculus that we know about it. One is that f prime of x will have to be 0 when x equals mu, the average, which again makes sense. That's going to be that maximum value. F double prime of x equals 0 when x equals mu plus or minus sigma. We could do this, and in our BC class we have. We find the derivative of this and set it equal to 0. And we find it's 0 when x is mu. We then find the second derivative and set that equal to 0. And we find it to be equal to 0 when x is mu plus or minus sigma. So we could verify this. It might be something you'd want to do on your own just to make sure it does work, but we're going to move beyond that and just use this and quite honestly, the calculator quite often. If I were to graph something like this, for example, let's just say I'm going to let x take on a normal distribution 10 to squared. That basically means that the mean is 10 and the standard deviation is 2. So if I were to pick some of these values, there's the mean 10, this is going to be 12, this is going to be 8. This is definitely not drawn to scale. I might pick some of these points just so I have a better feel for the graph. It's going to turn out to be my nice normal distribution. Now it's probably going to get closer a little bit more quickly, so there we go. But what we have are these very important key points. The derivative is 0 at the mean, and the second derivative is 0 at these 2 points of concavity. One standard deviation to the left and to the right. Now, without knowing anything else about this, and this is how you might have used this in previous courses, if I just section this off into these little pieces, we know something about the areas of each of these little sections. And more specifically, the area, let's just say between mu minus sigma and mu plus sigma, that's about, let's just say 68.26%. Most people would say it's about 68%. Depends on how specific you'd want to be. And then if we move 2 standard deviations, it's about 95 This one I always forget, about 0.44. And then we could continue to work with this. Some of you may already know that a lot of your testing is kind of based on this. If I were to do grades based on a normal distribution, of course, I would figure out the mean, the standard deviation, and I could section off where this might be a C, everything here in the middle. We'd have a D section, a B section, a little bitty A section, and a little bit you didn't quite make it section. We don't do it that way, but many times when you're judged relative to other people, that's kind of how it's done. So you can fit anywhere in this. Now, if we go back to this example, and I would ask you a few questions. For example, let's just say, what would the probability of that random variable be less than 12? Well, of course, I could just maybe use my calculator, which I'll get to in a minute, or I could realize that everything is symmetric with the mean. So this would be 34% about, and this is about 34. If this is all 50, that means everything here is 16. So the probability that something is less than 12 is going to be all of this area, which would be 100 minus 16, which is about 84. You could write 0.84 if you'd like. Another option could be maybe on an interval. What's the probability that it's going to be between 8 and 10? Same idea, I pretty much already have it for you. 8 and 10 is going to be about 34%. So whatever these mean and whatever I'm measuring and representing, I can find the probability of it being within a certain range. You notice I cannot find the probability of it actually getting 8. Theoretically, it would never happen. We only want to look at intervals. Now, if it happens to be a number that isn't so nice, like let's say the probability of the random variable being less than 11, then I'm going to have to use a calculator. There are other options we'll get to, but for now we'll use a calculator. And as far as the calculator goes, the syntax is going to be something like this. If you go into your distributions, you should be able to find normal, and there'll be a PDF and a CDF. What we want is the CDF. CDF is cumulative. PDF, remember, is going to be the individual one. And then we'd have to understand the syntax. Well, if I put 11, comma 10, comma 2, so it's going to be the mu and the standard deviation, this should give you my answer. I don't have a calculator up here with me, but you can go ahead and find that. If for some reason I wanted the probability on an interval, let's say from 9 to 11, no, 9 to 13. Write that. Then I would again use this normal CDF. But I'd have to put this interval and still 10, 2. Right? And that would give you what probability between 9, which is right here, and 13, which is up here. Now, if you, for some reason, wanted to find the probability that it's greater than 11, you would have to take 1 minus the probability it's less, because the calculator is always going to default to what's less than. So if I wanted greater than 11, I'd have to find 1 minus the probability that it's less than 11, because we know all the probabilities have to be 1. If I wanted to be outside of this range, of course, I would do the same type of thing. Take 1 minus whatever that answer is. Another type of problem that we're going to be facing would be one that maybe I wanted to find the number cutoff when you know the probability. For example, what's the probability that x is less than a if we know that happens to be, let's just say 16. So where is A going to be if the probability that it's less than A is 16? Well, you want to think of A as being kind of a vertical line moving back and forth. So if I want to find X is less than A, and A, everything to that side of it is 16%, we would realize it's going to be right here. Again, just because it's a nice number. A would be 8 in this case. If for some reason it's not a nice number, then we're going to have to use the inverse norm on the calculator. Now, one thing before I even do this, I want the probability of X is less than A to be 25%. I know that this is 16%. This would be 50, so I'm probably going to get a number right around here, probably less than 9. And in that case, you're going to have to use the inverse norm. And the syntax is also very similar. Let's see what we have. It's going to be basically that 0.25, and then of course our 10-2. Play around with that syntax and make sure that works on the calculator. I don't have it up here. I wish I could show it. The TI presenter on the computer kind of had an expired license, so I'm not able to work with that. But hopefully I can get that fixed soon. So that's basically the normal distribution. There's a lot more we could do with it. Read this text. Study the problems. Many of them are pure mathematical. Others are actual situations where maybe, again, we measure the height of all people, maybe in a school, and we found the mean, we found the standard deviation, which is just easy calculations, and then we would take some random person and maybe ask, what's the probability that this person would be between, 5, 10, and 6 foot, and we could find that. We could also find what is the measurement of a person in the bottom 25%. So where is that quartile? And that would be finding that A, that value. So good luck with this problem set from 29B. We'll be back early next week to standardize this normal, and we'll show you what that means then. All right, have a nice day and a good weekend, and keep working and keep staying in touch if you have any questions. Thank you.